Okay, we're back. Right, and now we're going to do question 17. So the mechanics question from paper 2. So the combined mass, right, so Lizzie is sat securely on a wooden sledge. Why do we need to know it's secure? Anyway, the combined mass of Lizzie and the sledge is m kilograms. So I've got my little copy of Lizzie here. So my mass acting downwards here is m. I'm assuming, right, and we've just mass times gravity is our weight coming down there. So we're just using G for gravity on this one. Okay, the sledge is being pulled forward in a straight line. So it's moving horizontally along a horizontal surface by means of a light, inextensible rope. So it's not stretchy. We don't have to look at the weight of the rope, which is attached to the front of the sledge. Okay, so the thing that's going to be pulling that then is this tension in this rope, isn't it? Which they're calling T. Right, okay, so straight away we can split that up into the vertical and the horizontal forces. So this bit here is opposite, so that's T sine theta. The horizontal force there is T cos theta. That's going up and that's going that way. Okay, otherwise that tension wouldn't be pulling in that direction. Right, the rope stays inclined at that acute angle, right, above the horizontal and remains taut. The sledge remains in contact with the surface throughout, so it's just moving horizontally along here. It's at no point going up or anything like that. Right. And Lizzie and the sledge move forward with a constant acceleration of a meters per second squared. Right. And the tension in the rope is constant. Okay, right, so the coefficient of friction between the sledge and the surface is mu, and there are no other resistance forces. Okay, so we've got the friction. Now friction's opposing the motion, and she's off that way. So let's have a look at what's going on. We've got the reaction force of, or the normal reaction, sorry, of Lizzie on the floor. That's, we're modelling that by coming out the top of her head. So resolving vertically, let's take up as positive. We've got R plus T sine theta, because that they are both acting vertically upwards, and they've got to be equal to what's acting downwards, which is mg. That weight there coming down. Okay. Now let's have a little bit. Okay, so and we move it. So let's do F equals ma now. Horizontally, the motion is horizontal, so F equals ma, we're going that way. Okay, so our positive force is T cos theta, because that's going in the direction of travel, and our negative force is the frictional force, so we've got to take that away, and that's equal to the mass, which is m, times our acceleration, which is a. Okay, now obviously we know that friction... Bye, love! Bye, love you. Friction is equal to mu times r. Okay, right. So our friction is equal to mu times r. Now, if you look over here, we haven't got a friction or an r in there. There's no friction and there's no r. So friction, how are we going to find this then? Friction equals mu times r. Now, r is equal to mg minus t sine theta, if we rearrange this one. So our friction is equal to mu times mg minus t sine theta. Okay, right, so I'm now going to put that, this one here, I'm going to replace that friction there with that. Okay, and hopefully that will start to look a bit like what we need. So let's have a look. Let's pop that in. So we've got T cos theta minus our friction, which is mu times mg minus T sine theta, is equal to ma. Okay, now this is starting to look very like what's going on up here. Okay, we just need to do a bit of rearranging. So clearly all your m terms need to be on one side and all your t's on the other. So let's expand that bracket. We've got t cos theta minus mu, that should be a minus, sorry, minus mu mg plus mu times t sine theta. Got a minus and minus, so that's making that a plus there. MA. Okay, so let's gather our t terms together. We've got t times cos theta plus mu sine theta. And let's get all our m terms on the other side. So all I'm doing is rearranging this now. Okay, and we're nearly there. So now to get t on its own, we're going to divide by cos theta plus mu sine theta. Let's take a factor of m out there on the top. So we've got a plus mu times g all over cos theta plus mu sine theta. And I think if we go up, m equals a plus mu g over cos theta plus mu sine theta. Boom! 7 marks. Ooh, yay! Okay, so have you, just ask yourself, have you done those 3 things? Have you resolved vertically? Have you done F equals ma? And have you done friction equals mu r? Those 3 equations give you everything you need there. Okay, right, so moving on. It is known that when m is 30, theta equals 30 degrees and t equals 40, the sledge remains at rest. Okay, so it remains at rest. Right, I'm just going to take this here and copy it down here, so we've got that there. Right, it is known that when m is 30, blah, 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 the sledge remains at rest. Uses these values to find the value for mu. Explain why her value for mu may be incorrect. Okay, so let's put these values in first of all and see what happens. Now, what we're saying, the sledge remains at rest. If something's not moving, the acceleration has got to be 0, so we can make that 0. Mu g, we can put that in there. And we've got cos 30 plus mu sine 30. So cos of 30 is root 3 over 2. And we've got mu times sine 30, which is just a half. Okay, right. So let's have a look. So at some point, something's not going to work out right, is it? So we've got 40 equals, expanding that top bracket at the top, you've got 30 mu g, and on the bottom, you've got root 3 plus mu all over 2. Now we know when we're dividing by a fraction, we can take that dividing by 2 up to the top and times by 2. So that will give us 40 equals 60 mu g over root 3 plus mu. Do we need to do this, or can we just solve it? Well, let's keep going. I'm just trying to think, is it because it's in equilibrium? Just having a look at those various components there. 40, no, that's all right. R will be positive, so that's all right. T cos theta will be, T cos theta would be 40 root 3 over 2, which is 20 root 3. So 20 root 3 minus is the frictional force going to be bigger? Anyway, I'll keep going. I'll keep going with what I'm doing because that would be the first thing that I would try and do. So 40, sorry, that 40 isn't over root 3 plus mu, is it? Okay, let's divide everything by 10, 20, 10, 20. So that will give us 2 times root 3 plus mu equals 3 mu g. So 2 root 3 plus 2 mu equals 3 mu g. Moving that onto the other side gives you 2 root 3 equals 3 mu g minus 2 mu. So 2 root 3 over 3g minus 2 is equal to mu. Now in this case, g is 9.8, so that's all right. So it's nothing to do with the calculation then. So I wouldn't worry about that. Why? The sledge remains at rest. I'm thinking if we did t cos theta minus friction equals ma, t cos theta, then we want that to be equal to 0, don't we, if we're doing F equals ma, and an acceleration is 0 because it's not moving. So if it's not moving, we can say that t cos theta will be equal to friction, because that's equal to 0. Does that matter? Okay, so we're told t is, so that would go to equals friction. So 20 root 3 equals friction. Why is that a problem? Is that a problem? Shh. Oh, shut up. Right, I'm going to have to come back to this.